What if you could literally pull electricity right out of thin air? Okay, well, maybe not thin air, but what about all that wasted heat? The stuff pouring out of our car exhausts in factories. We're going to look at a special device that does exactly that.
I mean, just think about it for a second. The heat coming off a car's exhaust, a factory smokestack, even your own computer's processor. It's a huge, totally untapped resource. And believe it or not, there's a whole class of devices designed to grab it.
Yeah, they're called thermoelectric generators, or TEGs for short. You can think of them like these silent, solid-state power plants with no moving parts. And today, we're going to crack open a brand new simulation to see just how engineers are pushing their performance to the absolute limit. So here's the game plan. We'll start with the core challenge, then look at a really clever solution, dive into some hard data, and wrap up with the critical trade-offs you have to make. All right, let's jump right in. Okay, Section 1, Power from Temperature Differences. So what is the fundamental challenge here when you're trying to turn heat into power? All right, before we go any further, there's one key term you gotta know, the figure of merit, which we just call Z. It's basically the go-to report card for how good a material is at this whole heat to electricity thing. A higher Z value, that means better performance. Simple as that. And right here, this is the main problem. The very properties that give a material that awesome Z value, they are incredibly dependent on temperature. So you can have a material that's a total superstar at converting low-grade heat, but when you crank things up, it might be completely useless. And this chart just lays it all out, doesn't it? It shows the problem perfectly. You've got one material that's awesome at low temps, another that hits its sweet spot right in the middle, and then a third that only really wakes up when things get super hot. So what do you do? Which one do you pick? Section 2, the segmented advantage. And the answer to that question is, what if you didn't have to pick just one? This is where we get to a really elegant solution to this whole material problem. So the solution is actually brilliantly simple, at least in concept. You don't use one material, you use a bunch of them. You basically build the generator's arms out of different segments, stacking these materials on top of each other. It's kind of like a thermoelectric layer cake. And the difference this makes, it's literally night and day. A standard TEG, it's stuck with just one material, which really limits its useful temperature range. But with a segmented one, each material gets to do its thing in its own ideal temperature zone. And what you get is a device that's super efficient across a way wider range of heat. Section 3, boosting power, losing heat. Okay, so that's the theory, right? But how does this actually perform in the real world? Well, let's dive into a deep computer simulation from the research to really see what we're working with here. So, the first big question they wanted to answer was pretty simple. What happens if we just make the hot side, well, hotter? They kept the cold side at a steady 300 Kelvin, which is basically room temperature, and just cranked up the heat on the other side. Okay, so at a hot side temp of 700 Kelvin, the simulation shows the device putting out about 2.1 watts of power. But then, check this out. They crank the heat all the way up to 1000 Kelvin. And the power output? It doesn't just go up a little bit. No, it skyrockets to 6.5 watts. Yeah, that's more than a 3x power boost. And this is so important. It's not a one-to-one relationship here. Pumping more heat into this thing gives you a dramatically bigger power output. If you're designing a system to capture waste heat, that right there is a game-changing piece of info. But hold on, the simulation didn't stop there. The researchers added something that a lot of theoretical models just ignore. A real-world factor, heat loss to the air around it. Simple convection. It's just the heat that naturally bleeds off the sides of the generator. And just look at the impact this has. In a perfect world, a vacuum with zero convection, the device hits a max efficiency of 11.4%. Pretty good. But once they add in a realistic amount of air cooling, that efficiency drops a full percentage point, all the way down to 10.4%. Now, I know what you're thinking. A 1% drop, that doesn't sound like a total disaster. But you have to understand, as the researchers themselves say, scientists in this field are fighting tooth and nail for every tiny fraction of a percent of improvement. So losing a full point just to the surrounding air, that is a huge deal and something you absolutely have to account for in a real-world design. Section 4, the final trade-off. And this brings us to the end, where the simulation revealed one last, fundamental choice that every single designer has to make. And here's the kicker. It turns out you can't have it all. You can't get maximum efficiency and maximum power at the same time. You've got to pick one. You can tune the device for max efficiency, which gets you a nice high voltage, or you can tune it for maximum power. Now your voltage will dip a bit, but your current, which is like the raw electrical muscle, jumps way up. It's the classic engineering trade-off. So let's wrap this all up. What are the key takeaways? Well, this simulation basically gives us a clear playbook. 1. Segmented designs are the way to go for wide temperature ranges. 2. More heat equals way more power. It's not linear. 3. Don't you dare forget about real-world factors like air cooling, because it will absolutely cost you efficiency. And 4. You have to decide what you want more: high voltage from max efficiency or high current from max power. You know, this kind of super detailed analysis, it gets us so much closer to making this whole waste heat recovery thing a real everyday technology. It really feels like the question isn't if we can do it anymore. The real question is, now that we know how to optimize them, where are we going to put these powerful little generators first? Where will we start reclaiming all that amazing energy we've just been letting slip away?